What if I told you that the fastest spacecraft humanity has ever built could reach Saturn in less time than it takes to complete a college degree? But the real answer to how long it would take us to get there is so much more complicated and so much more fascinating that it might fundamentally change how you think about space travel itself. Here's something that will absolutely blow your mind. When we talk about traveling to Saturn, we're not just talking about distance. We're talking about orbital mechanics, gravitational assists, fuel constraints, the actual position of planets at launch, and something called the tyranny of the rocket equation that makes interplanetary travel one of the most complex puzzles in all of science. The Cassini spacecraft reached Saturn in just under 7 years. Sounds simple, right? But here's the twist that changes everything. Cassini didn't travel in a straight line. It couldn't. Instead, it took a cosmic road trip that involved flying toward the Sun first, swinging past Venus twice, then Earth, then Jupiter, traveling over 2.2 billion miles to reach a planet that's only 746 million miles away at its closest approach to Earth. That's like driving from New York to Los Angeles by way of Tokyo, Sydney, and Cape Town. And that's just the beginning of how weird this gets. But before we dive into this mind-bending journey through space and time, do me a favor, smash that like button right now. Subscribe to the channel and hit that notification bell, because this is going to get wild. And I want to know, where in the world are you watching this from right now? Drop your country and what time it is for you in the comments. Are you watching this at 2 a.m. unable to sleep? During your lunch break? Let me know. I love seeing this global community coming together to explore the universe. All right, let's start with what seems like a simple question. How far away is Saturn? Right now, as I'm recording this, Saturn is approximately 886 million miles from Earth. But here's the first twist that most people don't consider. That number is completely meaningless for planning an actual mission. Why? Because by the time we could launch a spacecraft, Saturn will be somewhere completely different. And by the time that spacecraft arrives, Saturn will have moved billions of miles from where it was when we launched. Think of it like this. Imagine you're trying to throw a football to a friend, but your friend is on a different merry-go-round that's spinning at a different speed than yours. You can't just throw the ball at where they are. Now you have to throw it at where they're going to be when the ball arrives. Except in space, both merry-go-rounds are moving in ellipses, not circles, and they're moving at different speeds at different parts of their orbits. This is why NASA employs some of the most brilliant mathematicians on Earth, people like Dr. Robert Farquhar, who pioneered the concept of gravity-assist trajectories in the 1960s, fundamentally changing how we explore space. Let me give you the basic numbers first, then we'll break your brain with what they actually mean. Earth orbits the Sun at about 67,000 miles per hour. Saturn orbits at about 21,675 miles per hour. Earth takes 365 days to complete one orbit. Saturn takes 29.4 Earth years. Already, you can see the problem. These two planets are moving at vastly different speeds in vastly different orbits. Planning a trip between them isn't like planning a road trip. It's like trying to jump from one moving train to another moving train, where both trains are on different tracks, going different speeds, and you only get one chance to jump. The fastest spacecraft we've ever built that reached Saturn was New Horizons during its flyby in 2008. It passed Saturn's orbit at about 47,000 miles per hour relative to the Sun. At that speed, if you could fly in a straight line, you can't, but let's pretend. You could reach Saturn's average distance in about 20 months, less than 2 years. But here's where it gets interesting. New Horizons didn't actually visit Saturn. It just crossed Saturn's orbital path. The actual spacecraft we sent to Saturn Pioneer 11, Voyager 1, Voyager 2, and Cassini took very different routes and very different amounts of time. Pioneer 11, 6.5 years, launched April 1973, arrived September 1979. Voyager 1, 3 years, 2 months, launched September 1977, arrived November 1980. Voyager 2, 4 years, launched August 1977, arrived August 1981. Cassini, 6 years, 9 months, launched October 1997, arrived July 2004. Notice something weird? Voyager 1, launched in 1977, got there faster than Cassini, launched 20 years later with more advanced technology. How is that possible? The answer to that question is going to reveal something so counterintuitive about space travel that it stumps even science fiction writers. But first, we need to understand the most important equation in all of spaceflight, an equation so tyrannical that it has literally prevented us from exploring most of the solar system. Here's what will blow your mind. The biggest obstacle to reaching Saturn isn't distance, isn't time, and isn't even technology. It's mass. Welcome to what rocket scientists call the tyranny of the rocket equation. And it's the reason why interplanetary travel is so much harder than most people imagine. The rocket equation was formulated by Konstantin Tsiolkovsky in 1897, yes, 1897, before the Wright brothers' first flight. This Russian schoolteacher, working alone with just mathematics, figured out the fundamental limitation that still constrains us today. The equation is deceptively simple. Delta V equals V times ln MOM. Don't worry about the math. Here's what it means. And this is going to change how you think about space travel forever. To go faster in space, you need fuel, but fuel has mass. To carry more fuel, you need a bigger rocket. But a bigger rocket has more mass, which means you need more fuel to move that mass. But that additional fuel also has mass, so you need even more fuel to move that fuel. See the problem? You end up in an exponential nightmare where every kilogram of payload you want to send to Saturn might require hundreds or thousands of kilograms of fuel. Think of it like this. Imagine you're going on a cross-country road trip, but instead of gas stations along the way, you have to carry all the gas you'll need for the entire trip. But gasoline is heavy, so carrying all that gas makes your car heavier, which means you need more gas to move the extra weight of the gas. And that additional gas makes you heavier still, requiring even more gas. Pretty soon, your car would need to be mostly gas tank with just a tiny space for you. Now imagine that instead of 3,000 miles, you need to go 746 million miles. And instead of paved roads, you're fighting against planetary gravity wells. And instead of being able to slow down by using friction with the road, you need to use more fuel to slow down when you arrive. This is why the Saturn V rocket that sent astronauts to the moon was 363 feet tall and weighed 6.2 million pounds. But the Apollo spacecraft that actually reached the moon weighed only about 100,000 pounds. The rest? Almost entirely fuel. The rocket was 85% fuel by weight. And the moon is right next door, only 238,900 miles away. Saturn is over 3,000 times farther. Dr. John Houbolt, the NASA engineer who championed the lunar orbit rendezvous technique that made the Apollo missions possible, understood this tyranny better than almost anyone. He realized that landing the entire spacecraft on the moon and taking off again would require a rocket so massive it would be impossible to build. His solution, leaving most of the spacecraft in orbit and only landing a small module, saved the Apollo program. But for Saturn, even Houbolt's cleverness has limits. So here's the question that should be bugging you. If the rocket equation is so tyrannical, how did we send anything to Saturn at all? How did Cassini, weighing 5,600 pounds when fueled, possibly carry enough fuel to reach Saturn and then orbit it for 13 years? The answer is one of the most brilliant tricks in all of space exploration. And it's the reason why Voyager 1 reached Saturn faster than Cassini, even though Cassini was launched 20 years later. The trick is called a gravity assist, or a gravitational slingshot. And what if I told you that we basically steal energy from planets to accelerate our spacecraft. Here's how it works, and this is genuinely mind-blowing. Imagine you're on a skateboard and a truck drives past you. If you could grab onto the truck as it passes, it would pull you along, accelerating you to its speed. Now imagine you could then let go and keep that speed. You've just stolen kinetic energy from the truck. Though the truck is so massive, it doesn't noticeably slow down. Gravity assists work the same way, but instead of trucks, we use planets. When a spacecraft approaches a planet, it falls into the planet's gravitational well. As it falls, it accelerates, just like dropping a ball accelerates as it falls toward Earth. But here's the key. If you time it right and approach from the right angle, you can swing around the planet and fly back out, keeping all that speed you gained, plus getting a boost from the planet's own orbital velocity around the Sun. The planet is already moving at thousands of miles per hour around the Sun. When your spacecraft swings past it in just the right way, it's like a cosmic game of crack the whip. The spacecraft gets flung forward at a higher speed than it approached with. Dr. Michael Minovich, working at NASA's Jet Propulsion Laboratory in 1961, was the first person to fully work out the mathematics of gravity assists. He was a 25-year-old graduate student at the time, using an IBM 7090 computer to calculate trajectories that seemed impossible to the veteran engineers. They initially dismissed his work, but Minovich was right, and his calculations became the foundation for nearly every outer planet mission we've ever flown. This is why Voyager 1 reached Saturn faster than Cassini. Voyager 1 was launched during a rare planetary alignment that occurs only once every 175 years. NASA called it the Grand Tour Opportunity. During this alignment, Voyager could use Jupiter's gravity to slingshot toward Saturn, picking up enormous speed in the process. It approached Jupiter at about 35,000 miles per hour and left at over 47,000 miles per hour, gaining 12,000 miles per hour without burning a single drop of fuel. Cassini, on the other hand, was much heavier. It carried a probe to land on Titan, and it launched when the planets weren't aligned as favorably. So Cassini had to take a longer route, swinging by Venus twice, then Earth, then Jupiter, executing what's called a VVJGA trajectory, Venus-Venus-Earth-Jupiter gravity assist. This longer route took more time, but was the only way to give Cassini enough speed to reach Saturn with the fuel budget available. Now here's something that's going to completely reframe everything we've talked about. What if I told you that when we ask how long to reach Saturn, we're actually asking the wrong question entirely? Because the answer depends on something most people never consider, and it's something that could reduce travel time to Saturn to mere months instead of years. This is where most articles and videos about space travel lie to you, not intentionally, but by omission. They tell you how long it takes to reach Saturn, but they don't tell you the full story. There are actually two completely different questions. 1. How long to fly by Saturn? 2. How long to orbit Saturn? And the difference between these two scenarios is absolutely massive. Flying by Saturn is relatively easy. You build up as much speed as possible using gravity assists, and you go screaming past Saturn at tens of thousands of miles per hour, taking pictures for a few days as you zoom by, and then you're gone forever into deep space. This is what Voyager 1 and 2 did. They never slowed down. They reached Saturn in about 3 to 4 years, but they were traveling so fast that they had only brief encounters before flying away forever. But if you want to orbit Saturn to stay there and study it for years, like Cassini, did you face an entirely different problem. You have to slow down. And here's the brain-melting part. In space, slowing down requires just as much fuel as speeding up. Remember that there's no air in space to slow you down. Well, there's effectively no air until you're very deep in a planet's atmosphere. There's no friction, no brakes. The only way to slow down is to point your rocket engines forward and burn fuel to thrust in the opposite direction of your travel. Cassini carried about 3,000 pounds of propellant specifically for this purpose. When it reached Saturn after its 6.8-year journey, it had to fire its main engine for 96 minutes straight to slow down enough to be captured by Saturn's gravity. If that engine burn had failed, Cassini would have simply flown past Saturn and been lost forever. This is why Cassini took longer to reach Saturn than Voyager. It couldn't arrive going as fast because it needed to be able to slow down with the fuel it carried. Voyager didn't care about slowing down, so it could arrive much faster. Think of it like this. If you're driving cross-country and you just need to drive through a city, you can go on the interstate at 70 miles per hour. But if you need to stop in that city, you need to slow down much earlier. The trip takes longer because you can't maintain top speed all the way. Now here's where it gets really interesting. Dr. Robert Zubrin, aerospace engineer and founder of the Mars Society, has calculated that if we remove the orbit insertion requirement, if we just wanted to send something past Saturn as fast as possible, we could potentially reach Saturn in under a year using current technology with the right planetary alignment. But that's useless for science. It's like driving past the Grand Canyon at 100 miles per hour and trying to take a picture through your car window. Okay, so you might be thinking, why don't we just build faster rockets? Why mess around with gravity assists and slow orbital insertions? Just strap a massive rocket to a spacecraft and point it at Saturn. Here's what will absolutely blow your mind. Even if we had infinite fuel, which we don't, there are speed limits in space that have nothing to do with engineering. First, there's the speed of light, 186,282 miles per second. That's the universal speed limit, right? Nothing with mass can reach it, according to Einstein's relativity. At light speed, you could reach Saturn in about 67 minutes when it's at its closest approach. But here's the thing, we're not even close to worrying about the speed of light for interplanetary travel. Our fastest spacecraft, New Horizons, travels at about 36,000 miles per hour. Light travels at 670 million miles per hour. We're traveling at 0.005% the speed of light. It would take thousands of years of technological advancement to approach even 1% of light speed. So what's the real speed limit? It's something much more practical and much weirder. It's the speed at which your spacecraft can survive impacts from dust particles. In space, there's no such thing as empty space. The solar system is filled with dust microscopic particles left over from the formation of planets, debris from comets, and fragments from asteroid collisions. Most of these particles are smaller than grains of sand. At normal speeds, these particles are harmless. But here's the thing. Kinetic energy increases with the square of velocity. Double your speed, and the energy of impacts quadruples. At high enough speeds, even a grain of sand hits with the force of a bullet. Dr. Alan Stern, principal investigator of the New Horizons mission, has discussed this problem extensively. New Horizons travels at about 36,000 miles per hour, and even at this speed, impacts from dust particles are a serious concern. The spacecraft has shielding designed to protect it, but there's a limit to how much armor you can add before the spacecraft becomes too heavy. At speeds above about 50,000 to 60,000 miles per hour, the dust problem becomes severe. At 100,000 miles per hour, a speck of dust hits with the energy of a hand grenade. Your spacecraft would gradually get sandblasted to death. And it gets weirder. At even higher speeds, say, 1% the speed of light, 6.7 million miles per hour, individual hydrogen. Atoms in interstellar space would hit your spacecraft like cosmic radiation, gradually destroying it at a molecular level. This is something science fiction rarely mentions. There's a practical speed limit based not on your engines, but on your ability to survive the journey. But what if I told you there's a propulsion system, a real, scientifically sound propulsion system that could get us to Saturn in a fraction of the time, that completely bypasses many of these problems, and that we could build with current technology? It sounds like science fiction, but it's absolutely real. And the reason we haven't built it yet is going to make you question everything about how we explore space. Let's talk about the ways we could reach Saturn much faster, some proven, some theoretical, and some that will make you wonder why we're not already using them. Nuclear thermal propulsion. This isn't science fiction. We actually built and tested these engines in the 1960s and 70s. NASA's NERVA program, Nuclear Engine for Rocket Vehicle Application, demonstrated that nuclear thermal rockets work and could provide twice the efficiency of chemical rockets. Here's how they work. Instead of burning chemical fuel, you use a nuclear reactor to heat hydrogen to extreme temperatures and blast it out the back. Simple concept, enormous implications. Dr. Stanley Borofsky at NASA Glenn Research Center has calculated that a nuclear thermal rocket could reach Saturn in as little as 3 to 4 years, with direct trajectories, no gravity assists needed. More importantly, it would have enough power to slow down and orbit Saturn without the fuel constraints of chemical rockets. So why haven't we built one for interplanetary missions? Politics and public perception. The word nuclear scares people, even though these engines are actually quite safe and wouldn't pose a radiation risk to Earth. They'd only activate in space. But try explaining that to the public after decades of nuclear anxiety. Ion drives. Now this is technology we've actually used. The Dawn spacecraft used ion propulsion to visit the asteroids Vesta and Ceres between 2011 and 2018. Japan's Hayabusa missions used ion drives to visit asteroids and return samples. Ion drives work by accelerating ions, charged particles, to extremely high speeds using electromagnetic fields. They provide very low thrust, about the force of a piece of paper resting on your hand, but they can run continuously for years, gradually building up enormous speeds. Dr. Mark Raymond, chief engineer for the Dawn mission, often says that ion drives represent acceleration by patience. Dawn's ion drive could accelerate the spacecraft by about 60 miles per hour per day. That doesn't sound like much, but over months and years, it adds up to speed changes that would require impossibly large amounts of chemical fuel. An ion drive spacecraft could potentially reach Saturn in 4 to 5 years with more direct trajectories than gravity assist missions, and it would have plenty of propellant left to orbit Saturn and explore multiple moons. Solar sails. Here's something that sounds completely impossible, but actually works. You can propel a spacecraft using only sunlight. Light has no mass, but it has momentum. When photons from the sun hit a reflective surface, they transfer a tiny amount of momentum to it. Make the sail large enough and light enough, and you can actually accelerate a spacecraft using nothing but sunlight. No fuel required. The Planetary Society's Light Sail 2, launched in 2019, demonstrated that solar sail propulsion works in Earth orbit. Japan's Icarus spacecraft used a solar sail to fly past Venus in 2010. Dr. Les Johnson, a principal investigator for multiple solar sail projects, calculates that a large solar sail, perhaps a mile across, could accelerate a small spacecraft to high speeds over time, potentially reaching Saturn in 5 to 8 years. The advantage? Once deployed, the fuel is free and unlimited. The disadvantage? Solar sails work best close to the sun. As you get farther out, sunlight becomes dimmer, following the inverse square law, and the acceleration drops dramatically. By Saturn's distance, sunlight is 90 times dimmer than at Earth, making solar sails much less effective. Nuclear electric propulsion. This is the hybrid approach that could be our best bet for reaching Saturn quickly. Combine a nuclear reactor for power with ion drives for propulsion. The nuclear reactor provides steady, abundant electricity for years, and the ion drives convert that electricity into thrust. NASA has been developing this technology for decades. The Kilopower project recently demonstrated a small nuclear reactor that could power spacecraft systems. Combining this with ion drives could enable missions to Saturn in 3 to 4 years, with much more capability than current spacecraft. But here's where it gets really interesting. What if I told you that in the 1950s and 60s, scientists designed a spacecraft that could reach Saturn in just 2 years with the technology available at the time, and it could carry not just a probe, but an entire city's worth of people and equipment? This is Project Orion, and it's simultaneously one of the most brilliant and most insane ideas in the history of spaceflight. Here's how it worked. You build a massive spacecraft with a huge shock absorber plate on the bottom. Then you throw nuclear bombs out the back, detonate them, and ride the shock wave. One bomb every second or so, each one pushing you faster and faster. I'm not making this up. Dr. Freeman Dyson, one of the most brilliant physicists of the 20th century, worked on Project Orion from 1957 to 1963. He calculated that an Orion spacecraft could accelerate to 3% of the speed of light. That's 20 million miles per hour. At that speed, you could reach Saturn in less than a day. But even a more modest Orion design, using smaller nuclear explosions and accelerating to only 100,000 miles per hour, could reach Saturn with a crew in about 2 years without any gravity assists. The spacecraft would be enormous. Some designs called for ships weighing 10,000 tons, about the size of a large naval battleship. It could carry enough supplies, equipment, and people to establish a permanent base on Saturn's moons. Think of it like this. Instead of carefully calculating trajectories and rationing fuel like we do now, Orion would be like driving a monster truck through space. Brute force instead of finesse. The engineering was sound. Small-scale tests using conventional explosives proved the concept worked. Detailed designs were drawn up. It would have worked. So why didn't we build it? In 1963, the Partial Nuclear Test Ban Treaty prohibited nuclear explosions in space. Project Orion was canceled. The dream of rapid interplanetary travel died with it. Now here's the mind-blowing part. Everything we've sent to Saturn since then, every gravity-assist trajectory, every years-long mission exists because we banned the one technology that could have made Saturn as accessible as the moon. Dr. Dyson later said that abandoning Orion was giving up Columbus's sailing ships for fear of crossing the ocean. We chose caution over capability, and we've been paying the price in slow travel times ever since. But here's something that will completely reframe this entire discussion. We've been talking about how long it takes to reach Saturn, but we haven't addressed the elephant in the room. WH. Why does it matter how fast we get there? Is it just about getting there quicker? Or is there something deeper, something about human biology and psychology that makes travel time one of the most critical factors in space exploration? Let's talk about something rarely discussed in conversations about space travel. If we're going to send people to Saturn, the travel time isn't just a logistical challenge, it's an existential crisis. Every spacecraft we've sent to Saturn so far has been robotic. Robots don't care if the trip takes 7 years. They don't get bored, don't go crazy, don't need fresh food, and don't age. Humans? That's a completely different story. A 7-year one-way trip to Saturn means a 14-year round-trip minimum. Add time actually exploring Saturn and its moons, and you're looking at a 15 to 20-year mission. An astronaut who launches at age 30 returns at age 50. They miss their children growing up. They miss decades of technological advancement. Imagine leaving in 2005 and returning in 2025. You'd miss smartphones, social media, the entire modern internet. But it gets darker. Dr. Jim Logan, former chief of medical operations at NASA, has extensively studied the psychological effects of long-duration spaceflight. Based on data from astronauts on the International Space Station and Russian cosmonauts on Mir, he's identified something called the third quarter phenomenon. Here's how it works. When people undertake a long, difficult journey, they typically handle the beginning well. They're excited, motivated, focused on the mission. They handle the end well, too. They can see the goal. They know it's almost over. They find renewed energy. But something happens in the third quarter, roughly 60 to 75% of the way through the journey. That's when morale collapses. When depression sets in. When crew members start making mistakes, getting into conflicts, and experiencing the deepest psychological difficulties. For a 7-year trip to Saturn, the third quarter hits around year 5. You're so far from Earth that it's just a point of light. Saturn is still so far away, it doesn't look much closer than when you started. You're in a tin can, breathing recycled air, eating recycled food, with the same few people you've been with for 5 years, with 2 more years to go before you even arrive, and then you still have to do the mission, and then face another 7 years to get home. Think of it like this. Imagine driving across the United States, but the drive takes 7 years, you never stop. You never get out of the car. You can only eat what you brought with you, and you're doing it with 5 other people in a van. Now multiply that difficulty by 1,000 because you can't turn back. There's no AA to call if something breaks, and if you make one serious mistake, everyone dies. This is why speed matters so much for human missions. A 2-year trip to Saturn, if we use something like nuclear propulsion, is psychologically very different from a 7-year trip. A 2-year trip is doable. People have spent 2 years in Antarctica, on submarines, in isolated research stations. The psychological research shows that 2 years is just inside the range of what humans can tolerate in isolation. But 7 years? That's pushing the absolute limits of human psychology. Now let me tell you about an even more serious problem that makes travel time critical: radiation. In space beyond Earth's magnetic field, you're exposed to 2 types of radiation: solar particle events, sporadic bursts from the sun, and galactic cosmic rays, high-energy particles from deep space. Earth's magnetic field protects us from most of this radiation. On the International Space Station, which orbits inside Earth's magnetic field, astronauts receive about 200 to 300 millisieverts of radiation per year. For comparison, a chest X-ray is about 0.1 millisieverts. But in deep space, between Earth and Saturn, there's no magnetic field to protect you. Dr. Francis Cucinoda, NASA's former chief radiation health officer, has calculated that an astronaut on a Mars mission would receive about 900 millisieverts during the journey. That's equivalent to getting a full-body CT scan every week for 6 months. Now scale that up for Saturn. A 7-year journey to Saturn would expose astronauts to approximately 4,000 to 5,000 millisieverts of radiation. That's enough to significantly increase cancer risk, potentially cause cataracts, possibly affect cognitive function, and could even affect fertility. And here's the kicker. We don't have good shielding options. You might think, just build thicker walls. But that doesn't work as well as you'd hope. Traditional shielding materials like aluminum actually make things worse for cosmic ray radiation. When high-energy cosmic rays hit aluminum atoms, they create secondary radiation showers, like bullets fragmenting when they hit armor, creating more fragments that are also dangerous. The best shielding materials are hydrogen-rich substances like water or polyethylene plastic. But to provide meaningful protection, you'd need walls several feet thick, adding enormous mass to the spacecraft. Remember the tyranny of the rocket equation? Every kilogram of shielding requires more fuel, which requires more fuel to carry that fuel. Dr. Marco Durante, a radiation biophysicist at GSI Helmholtz Center, has proposed an elegant solution. Instead of blocking radiation, what if we use magnetic fields to deflect it, like Earth does? Create an artificial magnetic field around the spacecraft. This is theoretically possible, but it requires a lot of power, more power than solar panels can provide at Saturn's distance. You'd need a nuclear reactor, which brings us back to nuclear propulsion. See how everything connects? The faster you can get to Saturn, the less radiation exposure. Nuclear propulsion not only gets you there faster, but can also power protective magnetic fields. It's not just about speed, it's about survival. But here's something that's going to blow your mind. What if we've been thinking about this problem completely backwards? What if instead of figuring out how to get humans to Saturn, we should be figuring out how to bring Saturn to US. This is going to sound crazy, but stick with me. What if the future of Saturn exploration isn't about sending humans at all, but about sending something much better telepresence? Here's the concept. Instead of sending astronauts on a 14-year round trip, you send sophisticated robots controlled in real time by human operators on Earth. The robots are your eyes, hands and feet on Saturn's moons, but your brain stays safely on Earth. Wait, you're saying. We already do that with robots like Cassini and the Mars rovers. But here's the difference. Current space robots operate with significant time delays. Commands sent to the Mars rovers take between 3 and 22 minutes to arrive, depending on where Mars is in its orbit. The rover can't do anything in real time. It has to be programmed to act autonomously. For Saturn, the problem is much worse. Radio signals travel at the speed of light, and Saturn is so far away that a one-way signal takes 68 to 84 minutes, depending on orbital positions. That's over 2 hours for a round-trip communication. You can't drive a rover with a 2-hour control delay. You'd send a command to turn left, wait 2 hours to see what happened, and by then, the rover might have driven off a cliff. And this is the mind-blowing part. Dr. Kip Thorne, the same physicist who won the Nobel Prize and consulted on the movie Interstellar, has proposed a completely different approach. Instead of real-time control from Earth, you send a sophisticated AI-human hybrid system, a command ship in orbit around Saturn, filled with advanced virtual reality systems, and controlled by humans back on Earth, with only the 68 to 84-minute communication delay. Here's how it would work. The command ship has high-bandwidth communication with robots on Saturn's surface. No delay, because they're relatively close to each other. Humans on Earth put on VR headsets and control the ship's systems, seeing through the robot's eyes, but with an eye assistance that handles the immediate second-to-second control to compensate for the lag. Think of it like this. It's like playing a video game with lag compensation. The AI predicts what you want to do and executes it smoothly, but you're still making all the real decisions and experiencing everything the robots experience. This approach has massive advantages. 1. No human radiation exposure. 2. No psychological stress of years in space. 3. No life support systems needed. Robots don't need food, water, air. 4. If a robot breaks, you can send a replacement. You can't do that with a human. 5. Missions can last decades without aging human operators. They go home at the end of their shift. Dr. Simon Pete Worden, former director of NASA Ames Research Center, has called this approach the only realistic way to explore the outer solar system in our lifetimes. And here's the kicker. We could start doing this now. The technology exists. We just need to send the robotic infrastructure to Saturn, which takes 7 years with current propulsion. But once it's there, we could explore Saturn and its moons for decades using operators safely on Earth. Now let me tell you why all this matters, why Saturn isn't just another pretty planet to visit, but potentially the most important place in the solar system for understanding life itself. Saturn has 146 confirmed moons. One of them, Titan, might be the most Earth-like world in the entire solar system, and simultaneously the most alien. Titan is larger than the planet Mercury. It's the only moon in our solar system with a substantial atmosphere. In fact, its atmosphere is thicker than Earth's. Standing on Titan's surface, you'd experience 1.5 times Earth's atmospheric pressure, like being 15 feet underwater. But here's where it gets weird. Titan is so cold, about -290 degrees Fahrenheit, that water ice is as hard as rock, and methane and ethane, which are gases on Earth, are liquids. Dr. Sarah Hurst at Johns Hopkins University studies Titan's atmosphere and discovered something mind-blowing. Titan has weather. Not weather like Earth, but methane weather. Methane clouds form in Titan's atmosphere. Methane rain falls from the sky, collects in methane rivers, and flows into methane lakes and seas. NASA's Cassini spacecraft discovered that Titan has liquid lakes bigger than the Great Lakes, filled not with water, but with liquid methane and ethane. It has mountains made of water ice. It might have a subsurface ocean of liquid water beneath its icy crust. Think about that for a second. Titan has two separate systems that could support life: hydrocarbon lakes on the surface and a water ocean underground. It's like having two Earths in one moon, each with completely different chemistry. But here's what makes Titan absolutely critical for understanding life. It's a natural laboratory for prebiotic chemistry. Titan's atmosphere is filled with complex organic molecules, the building blocks of life. When Cassini flew through Titan's atmosphere, it detected hundreds of organic compounds, some so complex that scientists had never seen them form naturally before. Dr. Jonathan Lunine, a planetary scientist at Cornell and member of the Cassini mission team, calls Titan a giant frozen laboratory doing the experiments that might have happened on early Earth. On early Earth, before life emerged, our atmosphere was probably similar to Titan's, thick with nitrogen and organic compounds. But Earth's chemistry was disrupted when life evolved and filled our atmosphere with oxygen. Titan shows us what Earth might have been like before life, and what chemistry is possible in that environment. Now here's the mind-blowing part. Some scientists think Titan might actually have life, but life completely unlike anything on Earth. Life based on liquid methane instead of liquid water. Life that breathes hydrogen instead of oxygen. Life that would seem absolutely alien to us because it uses completely different chemistry. Dr. Chris McKay at NASA Ames has even calculated what metabolic signature such life would have. It would consume hydrogen gas and acetylene, both abundant on Titan, and produce methane. And oddly enough, Cassini's data showed that hydrogen and acetylene near Titan's surface are depleted in ways that match McKay's predictions. Is this proof of life? Absolutely not. There are non-biological explanations. But it's tantalizing enough that many scientists consider Titan one of the best places in the solar system to search for life. And this is why the question, how long to reach Saturn, matters so much. Every year we delay developing faster propulsion systems is another year we wait to answer one of humanity's biggest questions. Is Earth the only place with life, or is life common wherever conditions allow it? But there's another moon orbiting Saturn that might be even more likely to harbor life than Titan, and the discovery that revealed this possibility was so unexpected that it fundamentally changed how we think about where life can exist in the universe. Let me tell you about Enceladus, Saturn's sixth largest moon, and one of the most shocking discoveries in the history of space exploration. Enceladus is tiny, only 310 miles in diameter, small enough to fit inside the state of Arizona. It should be a frozen, dead world. Every model of planetary science suggested it would be just another boring ice ball. But in 2005, when Cassini flew past Enceladus, it discovered something that shouldn't be possible. Massive geysers of water shooting hundreds of miles into space from cracks in the moon's south polar region. Dr. Carolyn Porco, leader of Cassini's imaging team, described seeing the first images. We all just stared in disbelief. What we were seeing was impossible according to everything we knew. Enceladus is geologically active. It has liquid water under its ice shell, kept warm by tidal forces from Saturn's gravity. Those geysers are shooting water from a subsurface ocean directly into space. But it gets better. When Cassini flew through those geysers, analyzing the particles, it found 1. Salt, indicating the water is in contact with rock. 2. Organic molecules including complex carbon-based compounds. 3. Silica. Particles suggesting hydrothermal vents on the ocean floor. 4. Molecular hydrogen, indicating chemical reactions between water and rock. Let that sink in. Enceladus has all the ingredients for life. A liquid water ocean, energy from tidal heating, organic molecules, and most importantly, hydrothermal vents, the same kind of vents where many scientists think life first emerged on Earth. Dr. Hunter Waite, principal investigator for Cassini's mass spectrometer, analyzed the hydrogen measurements, and calculated that Enceladus's ocean has about the same chemical energy available as Earth's oceans. That's huge. On Earth, entire ecosystems thrive around hydrothermal vents in complete darkness, feeding on chemical energy rather than sunlight. Tube worms, crabs, fish, and bacteria live miles deep in the ocean, where no light penetrates, sustained entirely by chemistry. Enceladus might have the same thing. Right now, under that ice shell. And here's what makes Enceladus even more exciting than Titan. We don't need to drill through miles of ice to sample that ocean. The ocean is sampling itself for us. Those geysers are spraying ocean water into space, where we can fly through it and analyze it. Dr. Chris German at Woods Hole Oceanographic Institution put it this way. On Europa or Titan, we'd need to develop technology to drill through miles of ice to reach the ocean. On Enceladus, the moon is basically spitting ocean water at us. We just need to show up with a collector. Multiple mission concepts have been proposed to return to Enceladus with more sophisticated instruments. Some proposals include flying through the geysers dozens of times to collect material and search for unambiguous signs of life. Other proposals suggest landing near the geysers and directly sampling the material falling back to the surface. But all these missions face the same challenge. Getting to Saturn? A mission to search for life on Enceladus would need to reach Saturn 7 years with current propulsion, spend several years making multiple flybys of Enceladus, potentially land a probe, and transmit data back to Earth 84 minutes one way at light speed. We're talking about a 10 to 15-year mission minimum. Scientists working on such a mission might be retired or dead before it returns results. This is why propulsion technology is so critical. If we could cut travel time to Saturn from 7 years to 2 years using nuclear propulsion, we could launch an Enceladus life detection mission and potentially get results within a decade instead of 2 decades. The faster we can get to Saturn, the sooner we might answer the question, are we alone in the universe? Now here's something that's going to tie together everything we've discussed and completely reframe the question we started with. The time it takes to reach Saturn isn't just about distance or propulsion. It's about something much deeper that affects every space mission we've ever flown. Here's a question you probably never considered. Why did Cassini launch in October 1997? Why not January 1997? Or May 1998? Why that specific month? The answer reveals something profound about space travel that most people never think about. You can't just decide to go to Saturn whenever you want. The universe has its own schedule, and you have to work within it. This is called a launch window, and it's one of the most critical and most constraining factors in interplanetary travel. Remember earlier when we talked about how planets are like moving targets on different merry-go-rounds? Well, it turns out there are only certain times when you can efficiently jump from one merry-go-round to another. Launch windows depend on something called orbital mechanics. Earth orbits the Sun at one speed and distance. Saturn orbits at a different speed and distance. For an efficient trajectory one that doesn't require impossible amounts of fuel, you need to launch when Earth and Saturn are in just the right positions relative to each other. But it gets more complicated when you factor in gravity assists. Cassini's trajectory required flying past Venus, twice, Earth, and Jupiter in a specific sequence. This meant NASA had to launch when Venus was in the right position for the first flyby, 2, which would put Cassini in the right position for the second. Venus flyby 3, which would put Cassini in the right position for the Earth flyby. 4, which would put Cassini in the right position for the Jupiter flyby 5, which would put Cassini on course for Saturn. Dr. Louis DeMario, Cassini's mission design manager, has said that finding launch windows for complex gravity assist missions is like solving a multidimensional optimization problem where you're trying to align dozens of factors that are all constantly changing. For Cassini, there was a launch window that opened in October 1997. If NASA missed that window, the next opportunity wouldn't come for several years, and it might not be as efficient, meaning the mission might take even longer or require a bigger rocket. This is why space missions have launch dates that seem arbitrary to outsiders. They're not arbitrary at all. They're dictated by celestial mechanics. But here's where it gets really interesting. Launch windows to Saturn are actually relatively frequent compared to some destinations. There's a reasonable window to Saturn, approximately every 13 to 14 months. But the quality of those windows varies dramatically. Some windows offer trajectories that take 6 to 7 years. Others might take 10 to 12 years. Some allow for gravity assists that give you more speed. Others require more fuel. The Grand Tour window that allowed Voyager to visit Jupiter, Saturn, Uranus, and Neptune only happens once every 175 years. The last one was in the late 1970s. The next one won't occur until the 2150s. Think about that. There's a planetary alignment that makes outer solar system exploration dramatically easier, and it only happens every 175 years, and we just missed it in our lifetimes. Everyone alive today will be dead before the next one. This is why the Voyager missions were such a big deal. NASA had one shot, one chance in 175 years, and they had to take it. If they delayed or canceled the mission, everyone involved would have been long dead before another chance came. Now here's the mind-blowing implication. When we talk about how long to reach Saturn, we're not just talking about the transit time, we're also talking about when we can even launch. If you develop an amazing new propulsion system that could reach Saturn in 2 years, but the launch window doesn't open for 3 more years, your total mission time is 5 years, not 2. This is a constraint that most emerging space companies don't fully appreciate. SpaceX, Blue Origin, and others are developing new rockets and propulsion systems, but they can't change celestial mechanics. The planets move where they move, when they move, and you have to work within that schedule. Now let me tell you something that might make you frustrated. We could reach Saturn faster than we do. We have the technology. We've had it for decades. So why do we take the slow route? The answer is going to reveal something fundamental about space exploration that most people don't realize. It's not about what's possible, it's about what's affordable. Let's do some math that will blow your mind. The Cassini mission cost $3.26 billion over its entire lifespan, development, launch, operations. That sounds like a lot, but spread over 20 years, development and mission, it's about $163 million per year. That's less than the budget of a single Hollywood blockbuster movie per year. But here's the thing. Most of that cost was building the spacecraft and operating it at Saturn. The launch vehicle, the rocket that actually got Cassini off Earth, was only about $450 million, or about 14% of total mission cost. Now, if NASA had used a bigger rocket to send Cassini on a faster trajectory, skipping some of the gravity assists, the launch cost might have been $1 to $2 billion instead. That's 4 to 5 times more expensive for the launch alone, just to save a couple years of travel time. From a budget perspective, is saving 2 years worth doubling or tripling your launch costs? For a robotic mission that operates for 13 years once it arrives, probably not. Dr. Alan Stern, yes him again, once said something profound. In space exploration, patience is the cheapest commodity we have. Robots don't care if the journey takes 7 years or 2 years. They don't age, don't get bored, don't consume food. The operational cost of a spacecraft in transit is relatively low. You need some engineers to monitor it and occasionally send commands. But that's it. So space agencies optimize for cost, not speed. Gravity assists are free. They cost nothing but time. More powerful rockets and faster propulsion systems cost billions. Think of it like this. Imagine you're planning a road trip from New York to Los Angeles. You could fly there in 5 hours for $500, or you could drive there over 5 days for $100 in gas. If you're not in a hurry, driving makes economic sense. Space missions are the same way. Since robotic missions aren't in a hurry, slower and cheaper makes sense. But this calculation completely changes when you're talking about human missions. For humans, time is not cheap. Every day in space costs money and life support, increases radiation exposure, creates psychological stress, and risks crew health. For human missions, faster is actually cheaper in the long run, even if it requires more expensive propulsion systems. This is why NASA and other space agencies are suddenly interested in nuclear propulsion, which they largely ignored for decades. If we're serious about sending humans to Mars, or eventually to Saturn, we need faster transit times, and that means more powerful propulsion systems become economically justified. Here's the economic irony. We choose slow, cheap trajectories for robotic missions, but those slow trajectories are why we can't send humans. If we'd invested in faster propulsion decades ago, human missions to Saturn might be possible now. But we didn't, so they're not. It's a classic case of short-term thinking limiting long-term possibilities. Now I want to step back from the technical details and talk about what all of this means for you, yes, you specifically, watching this video right now. You live in a moment in human history that's absolutely unique. For 99.9% of human existence, Saturn was just a wandering light in the sky that moved differently than the stars. Ancient peoples noticed it, tracked it, wondered about it. Some civilizations worshipped it as a god. Then, about 400 years ago, Galileo pointed a telescope at Saturn and saw something he couldn't explain: bulges on either side. He didn't have the technology to see Saturn's rings clearly, but he knew Saturn was more than just a point of light. For the next 300 years, Saturn remained a distant mystery, studied only through telescopes, always too far away to truly understand. Then, in your lifetime, or maybe your parents' lifetime, or your grandparents' lifetime, everything changed. In 1979, Pioneer 11 flew past Saturn and sent back the first close-up images. A world that had been mysterious for all of human history suddenly became real. Not just a dot of light or a fuzzy telescope image, but an actual place with clouds and storms and rings made of billions of chunks of ice. Then Voyager 1 and 2 and 1980-81 revealed Saturn's moons in detail. Titan wasn't just a dot, it was a world with an atmosphere thicker than Earth's. Enceladus wasn't just an ice ball, it had mysterious terrain that didn't make sense. Then Cassini arrived in 2004 and spent 13 years turning Saturn from a planet we knew about into a place we truly understand. Cassini watched seasons change on Saturn. It discovered that Enceladus has a subsurface ocean and geysers. It landed a probe on Titan and saw liquid methane lakes. It revealed that Saturn's rings are dynamic, constantly changing, and might be relatively young. Do you understand how extraordinary that is? For 400 years, Saturn was mysterious. Then, in less than 50 years, less than a human lifetime, it became a place we know intimately. And you're alive for it. You're living in the generation that saw Saturn transform from myth to reality. Your grandparents' generation wondered what Saturn's rings were made of. Your generation KNOZS ice chunks, ranging from grains of sand to house-sized boulders, in rings so massive they could stretch from Earth to the moon, but so thin they're only about 30 feet thick in places. Now here's what I want you to really think about. Everything we know about Saturn, every image, every measurement, every discovery came from just 4 spacecraft that spent significant time there. 4. That's it. Imagine if Earth had only been studied by 4 visitors who made brief trips to a few locations. Imagine if all of human knowledge about Earth came from 4 tourists who visited New York, Paris, Tokyo, and Sydney. Would we really understand Earth? Would we have the full picture? Of course not. We'd be missing the Amazon rainforest, the Sahara Desert, Antarctica, the deep oceans, most of Asia, all of Africa, most of everything. Saturn has 146 known moons. Cassini studied maybe a dozen of them in any detail. There are over 130 moons we barely know anything about. Any one of them could harbor discoveries as significant as what we found on Enceladus. Saturn's atmosphere has storms larger than Earth, with winds over 1,000 miles per hour. We don't fully understand how they work. Saturn's magnetic field is weird, perfectly aligned with its rotation axis, unlike every other planet. We don't know why. Saturn's rings are disappearing, raining down onto the planet at a rate that means they might only last another 100 million years. In cosmic terms, we're seeing Saturn's rings right at the end of their existence. If humans had evolved 1 billion years from now, Saturn might not have rings at all. We're witnessing a temporary phenomenon, and we don't fully understand how or why it happened. There's so much we don't know, so much we need to explore. And the question, how long does it take to reach Saturn, isn't just a technical question. It's a question about your future and humanity's future. Let me put this in even more personal terms. Right now, you live in a world where Saturn is far away. So far that reaching it takes 7 years. So far that it feels impossible, distant, unconnected to your daily life. But think about how technology has accelerated in your lifetime. When the Cassini mission was being designed in the 1980s and early 90s, the internet barely existed. Cell phones were rare and primitive. Nobody had smartphones. Social media didn't exist. GPS was brand new and military only. Now, less than 40 years later, you're watching this video probably on a device more powerful than the computers that guided Cassini to Saturn, maybe while simultaneously messaging people on the other side of the planet with access to essentially all of human knowledge in your pocket. Technology accelerates exponentially. The propulsion systems that could reduce Saturn travel time from 7 years to 2 years aren't science fiction. They're science fact, waiting for funding and political will. If you're young, say, under 40, there's a very real chance that in your lifetime, you might see human missions to Mars. NASA targets 2030s to 2040s. Permanent bases on the moon already being planned. Robotic missions specifically searching for life on Enceladus or Titan. New propulsion systems that make Saturn significantly more accessible. Private space companies developing technologies that dramatically reduce launch costs. SpaceX's Starship, if it works as designed, will reduce the cost per kilogram to orbit by a factor of 100 compared to previous rockets. That's not a 10% improvement or even a 100% improvement. It's a 10,000% improvement in cost effectiveness. When launch costs drop that dramatically, suddenly missions that were impossible become possible. Multiple missions to Saturn become affordable. Bigger spacecraft with better propulsion become feasible. And here's what that means for you. The question, how long to reach Saturn, might have a very different answer 20 years from now than it does today. And the answer 20 years from now might determine whether you could ever visit Saturn or whether your children or grandchildren could. I'm not saying everyone will take vacations to Saturn. That's probably not realistic for centuries, if ever. But the idea that select humans, astronauts, scientists, explorers might reach Saturn within a human lifetime, that's moving from impossible to merely extremely difficult. And extremely difficult is something humans are really, really good at overcoming. Think about what drives human exploration and why you should care about it. We didn't evolve to care about Saturn. Evolution shaped us to care about finding food, avoiding predators, forming relationships, raising children. There's no survival advantage to wondering what Saturn's moon Titan smells like. Probably like gasoline. By the way, methane has a distinctive odor. But humans have this extraordinary capacity. We care about things that have no immediate practical value. We explore because we're curious. We explore because we're driven to understand. We explore because somewhere deep in our psychology, we need to know what's over the horizon. Even if there's no obvious benefit, this isn't practical or rational in a survival sense. But it's the most human thing about us. You personally will probably never benefit directly from studying Saturn. It won't make your life easier, won't pay your bills, won't cure your illnesses. But the fact that humans can look up at a speck of light in the night sky and say, I wonder what that is, and then spend decades and billions of dollars to find out, that says something profound about who we are as a species. We're the universe's way of understanding itself. We're the part of the cosmos that's become conscious and capable of studying the rest of the cosmos. When Cassini studied Saturn, it wasn't just a machine analyzing a planet. It was matter studying matter. It was the universe examining itself. And you're part of that. Every time you learn something about Saturn, every time you wonder about space, every time you ask, how long would it take to get there? You're participating in something bigger than yourself. You're participating in humanity's ongoing quest to understand reality. Carl Sagan said, somewhere something incredible is waiting to be known. That something might be on Enceladus. It might be in Titan's methane seas. It might be in Saturn's atmosphere or rings, or in one of the 130th moons we've barely studied. But we'll never know unless we go. And we can't go unless we solve the problem of how to get there. So when someone asks, how long does it take to reach Saturn? They're really asking several questions at once. How long with current technology? 6 to 7 years. How long could it take with better technology? Maybe 2 to 3 years with nuclear propulsion. Potentially months with more advanced systems we haven't built yet. How long will it take before we can send humans? That's not a question of physics. It's a question of investment, priority, and societal will. It could be 50 years, or it could be never, depending on choices we make now. How long before we truly understand Saturn and its moons? Decades at minimum, probably centuries, possibly longer. We've only scratched the surface. And perhaps most importantly, how long before the things we discover at Saturn fundamentally change how we understand life, planetary formation, our place in the universe, and the possibilities for humanity's future? That answer is, we don't know. But every year we delay developing better propulsion systems. Every year we delay missions to Enceladus and Titan. Every year we delay treating Saturn exploration as a priority. That's another year we wait for answers to some of humanity's biggest questions. Are we alone in the universe? How common is life? What forms can life take? How did our solar system form? Could humans eventually live beyond Earth? Saturn holds clues to all of these questions. Let me bring this to a close with one final perspective that ties everything together. Distance and time are related, but they're not the same thing. Saturn is far away. That's a fact of our solar system structure. We can't change that. But how long it takes to reach Saturn? That's not fixed. That's a choice. That's a function of our technology, our priorities, and our investments. Throughout this video, we've talked about the rocket equation, gravity assists, nuclear propulsion, ion drives, launch windows, radiation exposure, and economic constraints. All of these are real factors that affect how long it takes to reach Saturn. But the underlying theme is this: the time to reach Saturn is as much about us as it is about the distance. We could reach Saturn faster if we invested in nuclear propulsion. We could reach Saturn faster if we treated space exploration as a priority. We could reach Saturn faster if we were willing to accept certain risks. The fact that it currently takes 7 years to reach Saturn isn't because 7 years is some fundamental limit of physics. It's because 7 years is what we've chosen to accept given our current budget priorities, risk tolerance, and technological investments. And that means the time to reach Saturn can change. Will change if we wanted to. The generation that watched Cassini reach Saturn in 2004 was my generation. We saw a world transformed from a mysterious dot to an understood place. The generation that watches humans reach Saturn, or watches robotic missions confirm life on Enceladus, or watches permanent research stations on Titan, that might be your generation, or your children's generation, but only if we make it happen. So here's my challenge to you. The next time you look up at the night sky and see Saturn, and yes, you can see Saturn with your naked eye. It looks like a yellowish star that doesn't twinkle. Think about everything we've discussed. Think about the fact that it's 746 million miles away. Think about the fact that humans built machines that crossed that impossible distance. Think about the fact that those machines revealed worlds more bizarre and wonderful than anyone imagined. Think about the fact that we could get there faster if we chose to invest in it. Think about the fact that there might be life there, right now, swimming in Enceladus's ocean or floating in Titan's methane lakes. And think about this. You're alive at exactly the right moment in human history to potentially see these questions answered. Not your ancestors, not some future generation. You. The answer to how long does it take to reach Saturn is, it takes exactly as long as we choose to accept. And the answer to when will we discover life beyond Earth might be exactly when we decide to make it a priority. Before I end this video, I want to give you some actionable takeaways, things you can do that actually matter. 1. Support space exploration funding. Contact your representatives. Space agencies operate on budgets approved by governments. Public support matters. 2. Follow current missions. NASA's Dragonfly mission to Titan is scheduled to launch in 2028 and arrive in 2034. That's happening in your lifetime. Pay attention to it. 3. Learn more. The Cassini mission website has thousands of images and articles. Explore them. Let yourself feel wonder. 4. Share what you learn. Space exploration happens because people care about it. Make other people care too. 5. If you're young and considering a career, consider aerospace engineering, planetary science, or related fields. The people who will design the missions that reach Saturn faster are in school right now. That could be you. 6. Support private space companies that are working on reducing launch costs and developing new technologies. Their work makes everything more possible. 7. Think long-term. Space exploration is a multi-generational project. The missions you support today might not return results until your children are adults. That's okay. Invest in the future. Let me end with this thought. Right now, as you watch this video, there are spacecraft in development that will visit Saturn's moons in the 2030s and 2040s. Engineers are working on propulsion systems that will get us there faster. Scientists are planning experiments to search for life on Enceladus and Titan. The question, how long does it take to reach Saturn, has fascinated humanity since we first recognized Saturn as a planet. For most of human history, the answer was impossible. Then it became decades with theoretical technology. Then it became years with existing technology. Now it's 7 years, but could be less. What will the answer be 20 years from now? 50 years from now? That depends on choices being made today. Choices about funding, priorities, technology development, and risk acceptance. And in a democratic society, those choices are influenced by public interest and support, which means you have a say in how long it takes to reach Saturn. Not directly, not immediately, but cumulatively. Your interest matters. Your support matters. Your willingness to fund these missions through your taxes matters. Your vote matters. The time to reach Saturn isn't just a number in a mission plan. It's a reflection of our civilization's priorities and capabilities. And right now, at this moment in history, we stand at a crossroads. We can continue treating Saturn as a distant, optional curiosity, reached slowly and rarely. Or we can decide that understanding Saturn's moons, searching for life beyond Earth, and expanding humanity's reach into the solar system is worth investing in seriously. The technology exists or is within reach. The question is, do we care enough to use it? I hope I've convinced you that we should. Saturn isn't just a planet. It's a laboratory for understanding planetary formation, a potential harbor for life unlike anything on Earth. and a testament to how far human curiosity and ingenuity can take us. The journey to Saturn, whether it takes 7 years or 2 years, is a journey toward understanding our place in the cosmos. And that's a journey worth taking, no matter how long it requires. If this video blew your mind even a fraction as much as Saturn science blows mine, please hit that like button, subscribe to the channel, and share this video with someone who loves space, science, or just mind-bending facts about the universe. Drop a comment telling me, what surprised you most? What do you think we should prioritize in Saturn exploration? And would you take a 7-year journey to Saturn if given the chance? I'll be reading the comments and responding, so let's keep this conversation going. And remember, every time you look up at Saturn in the night sky, you're looking at a world we've actually visited, actually studied, and actually understand. That's incredible. That's a privilege. That's a gift from all the scientists, engineers, and dreamers who made it possible. Don't take it for granted. The universe is vast, mysterious, and waiting to be explored. Saturn is just one stop on humanity's cosmic journey. How long it takes to get there is up to us. Thanks for watching. Stay curious, keep looking up, and I'll see you in the next video.